Okay, the adiabatic process, when you're looking at the adiabatic process, you're assuming a couple things. You got to look at the atmosphere as being one blob of air, about a kilogram in mass, and it can't mix with its surroundings. So you're just kind of looking at one little portion. That's what makes it easy to look at the atmosphere, is to break it down that way. You do that a lot in science, where you have to break stuff down in order to really be able to look at it. And so that's what we're doing in the adiabatic process. We're looking at one little chunk of air when we're describing this. Now we've kind of hit these pieces already, but we're going through all this again, and hopefully looking at how clouds develop will be even more understandable, and you'll really have it down after doing this week's investigation lab. Now the adiabatic process, we're looking at no exchange of heat between the parcel and the environment. I mean, that little chunk of air. When you're talking about compressional warming, you're looking at the air going down, so sinking air. The parcel is sinking, it's going down from up above, down towards the surface, and it warms up when it does that. Expansional cooling would be the opposite. When your parcel's going from the surface and rising up to the atmosphere, it ends up cooling off. You can look at it like this, where you have the expansional cooling, where it starts, the parcel of air, the little blob, starts at the surface and goes up. Well, you see it gets bigger because the pressure decreases as you go up. So the pressure decreasing as you head up into the atmosphere means the gas is able to expand, or that parcel, what we're looking at, is able to expand because the pressure isn't pushing in on it. When that happens, as it rises up like that and it's allowed to expand, it ends up a cooling process, and the temperature ends up dropping for that parcel of air. Now, of course, the opposite, when you're talking about compressional warming, you're starting at the parcel is up above the surface where there's less pressure, so it's as big as it can be, and as it moves down to the surface, the pressure increases as you get closer to the surface, and that parcel gets pushed on and pushed on and pushed on. The more you push on it, the more friction you're getting. The more friction, the hotter it's going to be. So that's why compressional warming is where it ends up heating up. Now, with keeping all that stuff in mind, looking at lapse rates. Lapse rates are just temperature distribution with height. So you're looking at a profile of the atmosphere from the surface all the way up to, well, however far your instrument's going to take the measurements. For our purposes, obviously, we look at stuff in the troposphere because that's what we need for the weather. Anything above that, then it's, you're not looking at weather, you're looking at other things in the atmosphere going on. So a lapse rate is different in different areas, so it's not the same as you go across the world, but for like an average normal environment, then we roughly say it's about 6.4 degrees Celsius per 1,000 meters as you go up. That's what the temperature drops as you go up. Again, it's different in different areas because of location, because of things like more water vapor, less water vapor, that kind of stuff can make it be different. But that's a good average for most. In the lab, we're going to use 6.5 on some things because, well, it'll be easier. We'll round up or down so that way you don't have to worry about the decimal points, just to kind of get the idea. But remember, these are the UV diagrams. So you're looking at a profile of the atmosphere. This is a real simplistic looking one. But you can see as you go up, this lapse rate, this temperature profile, if you want to look at it like that, is dropping 6.4 degrees per 1,000 meters. If you're looking at dry air, meaning like absolutely no water vapor in it whatsoever, which is, happens in different places. Okay, if you're looking at dry air with no water vapor in it, then roughly the temperature is going to drop about 10 degrees Celsius per 1,000 meters as you go up. So they call it dry adiabatic lapse rate, meaning there's no moisture involved. Now, of course, if there is moisture involved, then the air is going to cool at a different rate. And these are, again, rough depending on where you're at, how much water vapor is present, that kind of stuff. But these are good estimates to use. Let's see, 5 degrees Celsius per 1,000 meters is what the air would end up dropping if that air was saturated. So if you're looking at a temperature profile and where it's dry, meaning the temperature and the dew point are not together, you would use a dry adiabatic lapse rate. Once the temperature and the dew point were the same, so the air is moist, then you would use a saturated adiabatic lapse rate. So keep that in mind when you're looking at the lab. There'll be times when you're looking at it for dry air versus moist air, and you have to make sure you use the correct lapse rate with it. Now, kind of a crude example would be looking at a mountain effect, like a windward side and a leeward side. The windward side, where the wind is obviously coming on, and you're looking at the mountain, the wind would strike the mountain, it has to force the air to rise, and you'd have expansional cooling on one side of the mountain, and then once that air reached the summit and then extended its way back down the mountain, then it would be compressional warming. So here's an easy way to look at it, where we've got an air parcel at the ground, 30 degrees Celsius, goes up 1,000 meters, and we're using, in this case, just the dry. So 10 degrees Celsius per 1,000 meters is what it's going to drop. So go from 30 to 20, go up another 1,000 meters, it drops to 10. Now let's say that, let's say for this example that the dew point is 20 degrees Celsius. So once you go from the air parcel to the surface, you drop it 10 degrees dry, because it, if it's 30 temperature and dew point's 20, they're not the same. Once you go up 1,000 meters, then the temperature and the dew point's going to be the same. So this would be the base of the clouds in this example, because the temperature and the dew point are the same. So you have 100% relative humidity, and the cloud would end up forming because you would have condensation at this point. So if we were going to raise the air again above this, we'd have to use the saturated adiabatic lapse rate, because it's now saturated. The temperature and the dew point are the same. So if we were to do that again, we would raise it up one more time up to this 2,000 level, and we would use that 5 degrees Celsius per 1,000 meter drop. So we would go from 20, and then it would be 15 degrees Celsius. And if we were at 15 here, let's say we were going to take it up one more time, we're going to go up to the 3,000 meter level, which isn't listed on here, but let's say if we did, we would still be dropping it at the 5 degree rate. So then we would go from the 15, and then it would be 10 up here, the 3,000. Now if we were going to take this and go down, then if you're going down, you're going to use the dry adiabatic the entire time. So let's say we go back to that example where this is 15, because we went from 20 and we dropped it the saturated adiabatic lapse rate, which made that 15. So we'll go back to that example where that's 15. And then if we're going to have it go compressional warming, let's say we're at the top of the mountain, now we're going to go down to the other side of the mountain. Well, we're going from less pressure to more pressure, so it's going to increase. And so we've taken all the moisture out at this point, because the cloud base was at the 1,000 meter level. So we don't have any moisture, so we're going to have it go back down the dry adiabatic. So remember, this was 15. Then we're going to go down to this one, 15 plus 10 is 25, plus another 10 would be 35. So on that other side, it would be 35 degrees Celsius on the other side of the mountain, which is 5 degrees more than our starting point. So it compressed and it warmed up, and so that's how it works. Of course, that's a very simplistic example, but one side of the mountain is going to be cooler, and the other side of the mountain is going to end up being warmer. And in this case, that's what ends up working. And the next thing to look at would be stability, and you can figure that out by looking at Stuvie diagrams. When air is unstable, air is rising, which means you can have cloud development if you have enough moisture. You can have precipitation, there's enough moisture as well. Air that is sinking, so the air that's going down, the compressional warming portion, is what they call stable air. Stable air is going to resist cloud development and generally be cloud-free and nicer weather. Whereas you're talking about precipitation of some kind, possibly, or just even clouds on the unstable side. If you're neutral air, then it means that you can go either way. Right now, the air isn't rising, it isn't falling, but anything that moves in could disturb that and send it one way or the other. So neutral air can also be good for thunderstorm development in the spring and summer situations, because you can easily make it go from one way or the other. All you would need is lots of sunshine to heat up the atmosphere, and then boom, it goes from neutral air to unstable air. So that's what it looks like when you're just kind of talking about whether it's stable or unstable. Now, actually applying it to Stuvie diagrams, when you look at them, on them, you're always going to look at the temperature profile. So the temperature profile is usually always the one that's to the most right of the two. Sometimes if you look at different maps, they actually have them color coded, one color versus the other, but it's always the rightmost line is the temperature profile. So if you look at the temperature profile, if it skews off to the left, then it's unstable air, which means the air is getting colder. If it skews off to the right, it's stable air. If it's somewhere in between there, then it's what they would consider neutral. Okay, so next couple studies we can look at several different things with them. Whenever the two lines are close together, it means that there's more moisture. If the temperature profile line is going off to the left, it's unstable. And then you can also look at it in terms of whether it's going to be rain, snow, freezing rain, or sleet, if you're going to have precipitation anyways. The 0 line is right here, so that's the freezing point, and you can tell that most of the temperature profile is below freezing except for this little tiny portion that's just above freezing. So in this situation, if precipitation was going to fall, you're probably going to see it as a pretty wet snow, because it'll be able to melt just a little bit, so it's going to be more snow than it is anything. That's why I'm saying it's going to be like the big flakes, the more wet snow. The next one, the temperature and the profile line are really far apart. That tells you it's extremely dry air. In this case, if it were to fall as precipitation, obviously here's the 0 line, all of it's going to be in the form of rain. And in this case, it'd be all rain. And this one, especially looking at the very lowest layers for your stability, it's neutral. It's not really going off to the left really great, it's not going off to the right, so it's kind of in between. That would be a neutral. So nothing really going on there. This profile has the two lines basically look like they're together, so extreme moisture is in that area from the surface all the way up to about 700, 650 or so. So lots of moisture involved at this location. And it's skewing off kind of to the left, so it's more of kind of an unstable example. Let's see, this one here, again, temperature is going to fall as, or the precipitation is going to fall as rain. You can see that at the surface it goes off to the right, so this one's really stable. So this one's resisting motions for air to rise. Everything is sinking. This last one, the moisture content is, it's a little bit moist. It's not super dry or anything, but the two aren't together, so it's not obviously really, really moist there. Everything's below freezing, and that would indicate that everything, if there was precipitation, would follow snow. This is actually the one for Denver, so note that the surface for Denver starts up a lot higher because it's the mile-high city. And so you notice that maybe on a lot of them where it doesn't exactly start right here down at the bottom is average is what you consider 1,000 is the surface for most places, but obviously not all of them. So that's what you're looking at for diagrams and how those kind of fit into it. For precipitation, we were to look at that at the real thing, but here's another way of looking at it more simplistically. You're going to get all rain here, because most precipitation, remember, starts as snow. Eventually it'll turn over to rain if it's above freezing close to the surface. If the temperature profile is below 0 all the way, like the Denver one, it'd be all snow. If you had an in-between where it's cold, gets warm, and then freezes again well before the surface, then that would be sleet. If you had it start as snow, it would melt, and then right at the surface is freezing, and that would be a freezing rain example. Here are some clouds that are precipitation producers, and we'll just kind of end this here looking at the types of clouds that can produce precipitation.